Hi, this is James Howard, and this is my video walkthrough of the code that I wrote for the cs7375 second programming assignment, the solving the 8 puzzle problem using the A-star algorithm. So the code is similar to for the first assignment. Starting off, I have a board class, and I've created a class variable goal to represent the goal state, so that every instance of the board class will have access to this variable. And again, I've just represented the 8 puzzle tile as a two-dimensional array, and this is what the goal array looks like, the goal 8 puzzle tile. I have a constructor here. It's going to take in an arrangement, which is going to be an array like this, the parent of this particular board, and the depth of this board as it gets searched down through the graph. And so we just set those initialized variables, and then we set this estimated cost variable to the depth plus the get Manhattan distance function, which we'll look at in just a minute. The idea there being that the depth is going to be the cost to get to this node, and then the Manhattan distance is going to be the heuristic of how far away this node is from the goal node. Just like in the first assignment, this is a built-in that I'm overriding to create a better string representation when you print excuse me, one of these boards. This is overriding the hash built-in, which enables you to put boards on a set, making them easier to search when you're trying to determine if they've already been explored. And inside of that, we're just creating a tuple of tuples out of the array of arrays. It's just a little hashing trick. This is overriding the equality built in so that we can compare the board to the goal state board to see if the board that you just created is the goal. And basically all it's doing is walking through the array and through the inner array and checking to see if every arrangement, if every tile excuse me, is the same as the one that you're comparing to. And if it is, it's going to return true, otherwise it's going to return false. Overriding the less than built in here, and this is so that you can put these boards on a priority queue, which is what I did to implement the A-star logic, and same with the greater than built in here. And essentially we're just saying if the estimated cost is less than the compared what the board that you're comparing it to estimated cost, or greater than its estimated cost, that allows these boards to bubble up to the top based on their estimated cost. Copy arrangement simply takes in the current board and creates an arrangement of array of arrays exactly like the current board. Get children starts off, this is exactly like in the first programming assignment, starts off by figuring out where the location of the blank is on the board. So it's got the blank row and the blank column, and the row count, and it gets the row count and the column count, and that's how it determines what the possible children are, branching off from this particular board. And it just walks through the blank row minus 1 blank column, the blank row plus 1 blank column, blank row plus blank column minus 1, blank row blank column plus 1. So that will represent all the spaces around the blank, and then it checks to see, okay, is this a valid space? And if so, then essentially what you're doing is swapping the positions of the ones that you're iterating through with the blank space. And then we're creating a new board with that new arrangement and giving it a depth of the current board's depth plus 1. And then just returning all those potential possible moves. This is the function for getting the location of the blank. It just walks through the arrays until it finds the blank and then it returns that position. This is the get Manhattan distance function, and essentially what it's doing is creates a distance variable, sets it to 0, and then it says for each tile in the board, if it's not a blank, then get the distance of that tile, so that calls this function down here. And what this function does is just walks through. It's taking in the position of the tile that you're working on. It says check to see if where that same number appears in the goal state, and then gets the Manhattan distance, which is going to be the absolute value of the goal position minus the position that you passed in plus absolute value of the goal position, the horizontal and the vertical positions of the goal position. So that's how you get the Manhattan distance. It's like you go over X and go down Y. So that's it for the board class. Then we have this solver class, which is where the actual work is being done. And so this is going to be initialized with a starting board and a goal board. And then it's going to, when the solve is called, it's going to run this A star method. And so we're using the priority queue, as I said before, sending the friends to that priority queue, putting the starting board on the queue, and then I'm putting a print here just to show that that's where the first one that we're starting with. This explored set is just going to keep track of any that we've already explored. And then we say while the priority queue is not empty, essentially, then we're going to get the top one. And remember that the queue, the boards are going to be ordered by their estimated cost, which is the cost to get to the particular node plus the heuristic of getting from that node to the goal based on how far each of the tiles of that board are from their goal state. And then we say if the current is equal to self.goal, then we return current. Otherwise, we're going to add that one to the explored set, and then we're going to get all the possible children from that current state. And if we haven't already explored the child, we're going to print it, and then we're going to put it into that priority queue, and it'll be sorted automatically. So down here I've got a starting state, which is the same as from the assignment sheet. The goal state is, of course, creating a new board using that board.goal class variable as the arrangement, which again is up here. And then we're creating a solver, passing it that start and goal, and calling solve. And then I've just, to print the most direct solution that it finds, I've kind of separated that with this print solution statement, and then I'm going for through each step in the solution and printing off that statement. And essentially the way that works is after finding the solution, I create this path that goes back through the solution and looks at each board's parent to get from the solution, from the goal node back up to the root. So if we run this, I'll open this in a text editor so we can see the results. So again, this is all of the board states that were added to the fringe, and then this is the actual solution that the algorithm found, and you can see it took it 6 steps to get from the starting state to the goal state. And that is all. Thank you.